We'll continue with more on rigid body mechanics. But even before I proceed, do you have any doubts on the concepts that have been covered so far? Let me be very specific. Do you all understand rigid body considerations and the kinematic standpoint of rigid body considerations? Relative velocity along the line joining any two particles 0. Do you understand that rigid body motion could be imagined to be constituted of two elementary motions? Pure translation, in which every particle shares a common velocity with the center of mass, plus superimposed with pure rotation about the center of mass, right? And therefore, with this, you could compute the velocity field in the surrounding region, right? By superimposing pure translation with pure rotation, a vector sum of these two effects could lead to the velocity of any particle that constitutes the rigid body, or if you imagine the outside also to be extended part of the planar body, you could compute the velocity of such particles. The concept of instantaneous center, where this composite motion could be imagined to be just pure rotation about the instantaneous center, in which the velocity field could be computed just by looking at the instantaneous center at a given instant. Imagine every particle to be moving in a circle of radius equal to its distance from the instantaneous center and velocity perpendicular to the line joining this. To locate the instantaneous center, all that you needed to do was have knowledge of the direction of velocities of any two particles, draw perpendiculars to these directions. The point where this perpendiculars intersect would be the instantaneous center for that general rigid body motion. The instantaneous center could be on the rigid body or could be a point outside the rigid body, right? General rigid body motion could have acceleration, which is characterized by rate of change of velocity of the center of mass, and then it could have angular acceleration, which is rate of change of omega with time, right? So, and also computation of omega given the velocities of any two particles. All that was required to be done was take relative velocity perpendicular to the line joining the two particles, divide by the separation between them, and that's going to give you the omega of the rigid body. Basic issues related to computation of moment of inertia, related to kinetic energy in pure translation, pure rotation, and general rigid body motion, right? Following this, the notion of torque, to obtain the torque about a point, the fact that the torque about any point on a line joining the line of action of the force will be 0. The torque about any point on a line parallel to the line of action of the force would be the same, right? And all that required for the torque was the moment arm, and we would normally talk of either a clockwise torque or an anti-clockwise torque, because we would stay put with a planar motion, and therefore the sense of the torque would be more important than the actual direction to get a physical feel for torque. Very similarly, we landed up understanding the concept of angular momentum, computation of angular momentum for pure translation, pure rotation, and for general rigid body motion, the concept of the impulse, the angular impulse, linear impulse into arm would give you angular impulse, and whereas linear impulse led to change of linear momentum, angular impulse about a given point led to change of angular momentum about that point, right? And what was very important was the computation of the angular momentum about a point, which depended on where that point. It had two constituents. One, which did not depend on where that point was located, that ICM omega. It could be clockwise or anti-clockwise based on whether omega was clockwise or whether omega was anti-clockwise, right? And then there was a MVR kind of a thing, MVD kind of a thing, where D was the perpendicular distance of the line of linear momentum from the point about which angular momentum was computed. This MVD depended on where the point was. It could be clockwise or anti-clockwise. The net would be the algebraic sum of ICM omega and MVD, One could be positive, one could be negative, both could be positive, both could be negative, depending on our choice of sign for a given sense. Right? Conservation of angular momentum. Conservation of angular momentum. That means, and also I told you that internal forces produce no net torque about any point. Produce no net torque about any point. So if there was a collection of particles that were mutually interacting, because of those mutually interacting forces, there was no torque produced, no net torque produced about any point in the region. Whereas external forces could produce torque, and if the net torque about a point, net torque because of all the external forces put together about a point was 0, then it led to a very important conservation principle, conservation of angular momentum, right? And we looked at some illustrations related to that, in which the conditions for translation, the conditions for rotation, and the constraints were all deployed. And as and when required, the conservation principles were deployed. The conservation of linear momentum, conservation of angular momentum, and so on and so forth, right? So this is the summary of the story that we have covered this far. Now, based on these ideas, so whatever we do essentially will be all based on what we have done so far. So if you have a complete grip of these basic elements that we have covered, then you are in good shape. All right. Now, suppose there was a horizontal surface on which this hexagonal body was resting. A, B, C, D, E, F were the vertices, or we can refer to this as the nodes of the hexagonal body, right? And this was a rough surface, say, rough horizontal surface. Say this body was in a state of toppling about A. Say it was toppling about A. It was witnessed to be toppling about A, right? Now, some simple considerations. While it was, and let's say, the center of mass of this body was this. This was its center of mass. Okay. Now, during toppling, what was B doing? B, while it was toppling about A, that is, when it was toppling about A, you realize that B would be moving in a circle of radius A centered at A? Yes or no? B would be moving in a circle of radius A centered at A, and this would be the next position of B. B prime would be the next position of B, next perceivable position of B, right? So during toppling, B, for example, moved in a circle of radius A centered at capital A. Centered at capital A. Right? Now, this surface, let's say, was a fixed horizontal surface. This surface, let's say, was a fixed horizontal surface. Clear? Now, the point A had no relative. Point A was the point of contact during toppling. During toppling, point A was the point of contact. POC, let me call it the POC, the point of contact during toppling. Point A was the point of contact during toppling, right? And there was no relative motion between A and this fixed surface during toppling, right? So, no relative motion between A and the surface. No relative motion between the point A and the surface while toppling was taking place. While toppling was taking place, right? And if there was no relative motion between A and the surface, what would have been the nature of friction between between A and the surface? Therefore, the nature of friction must have been static. Would have been static. Nature of friction would have been static. It could have been anywhere from 0 to mu times n. Anywhere from 0 to mu times n, right? It will always be a challenge to be able to deal with static friction, because unlike kinetic friction, which has, let's say, a fixed value, approximately maximum static friction or slightly less than that, static friction can have very many values, 0 to mu times n. All these would be acceptable values of static friction. So every time you know that this is a situation involving static friction, you will have to invite and invoke indirect means to be able to compute the value of the static friction. Again, if it is about kinetic friction, then I would know the direction of relative motion, and I know that the direction of kinetic friction would be opposite to direction of relative motion. Therefore, to obtain the direction of kinetic friction is straightforward, but to be able to obtain direction of static friction, not that straightforward, right? For that also you would have to deploy some other means. We'll figure out as we chug along how to obtain the direction and the magnitude of static friction as and when prevalent. Now, during toppling, the static friction acts through A, right? Line of action of static friction passes through A, yes or no? And the point A at which static friction acts, the point A where static friction acts, does not get displaced during toppling, yes or no, right? Okay. So, during toppling, A does not get displaced. Therefore, the work done by static friction must be 0. Work done by static friction must be 0, yes or no? Right? If the work done by static friction is 0, it does not lead to change of kinetic energy. Yes or no? It does not lead to change of kinetic energy. Change in kinetic energy because of static friction will be 0. It will act. But since it's not doing work, from work energy perspective, no change of kinetic energy would be brought about owing to presence of static friction. Right? Or delta Ke because of static friction alone, because of friction alone is 0, even though it's there. It's not instrumental in bringing about change in kinetic energy. That's work energy theorem. Right? Yes or no? Right? In fact, all points on this rigid body at this during toppling seem to be moving in circles centered at a with radius equal to the corresponding distance. For example, E moves in a circle of radius EA centered at A. D moves in a circle of radius DA centered at A. And yes or no? Right? The point A is at rest during toppling. The point of contact is at rest during toppling if this surface is fixed. Right? Which means A must be the instantaneous center at during toppling. The point of contact must be the instantaneous center during toppling. Yes or no? Right? Instantaneous I can imagine the entire rigid body to be in a state of pure rotation about A during toppling. Yes or no? Right? So work done by static friction is 0. No relative motion between A and the surface. Right? Frictional force that acts through the point of contact does no work. Therefore produces no change of kinetic energy all by itself. Right? And the point A acts as the instantaneous center during toppling. Right? So these are some of the things that happen during toppling, right? These are some of the things that happen during the toppling process. Now, so the first site of toppling is A. And then you would expect B to be the next site of toppling, then C to be the next site of toppling. Successively, you have discrete sites of toppling. A, B, C, D, E are discrete sites of toppling. A, B, C, D, E, F, and then A, B, C, D, E, F. This is the order in which toppling occurs discretely at these vertices or nodes, right? No torque produced by friction about A is 0. No, but other forces could produce. I am not showing other forces that are producing this toppling. I am not talking about the causes of toppling right now. I am only studying toppling. Right? Now, this is a hexagon, right? If I increase the number of sides of this polygon, if I increase the number of sides of this polygon, there would be more sites of toppling, right? Yes or no? If it becomes a 8-sided figure maintaining, let's say, the same perimeter, then there would be more frequent sites of toppling. There would be more frequent instances of toppling, yes or no? Right? 10 sides, even more frequent sites for toppling, even more frequent toppling takes place, right? If n are the number of sites, and as n increases, toppling becomes more and more frequent. Toppling becomes more and more frequent. Yes or no? as n tends to infinity, the polygon becomes a circle. With how many vertices? Infinite vertices, with infinite vertices. Right? A1, A2, A3, An, A infinity. Right? Every point of the circle is a vertex of the polygon. Every point of the circle is a vertex of the polygon. What is then produced is still toppling, but now continuous mode of toppling results. As n tends to infinity, the nature of toppling becomes continuous. This was discrete mode of toppling, but as n tends to infinity, toppling becomes continuous. Right? Or as n tends to infinity, what's produced is a continuous state of toppling. Right? Toppling occurs at every point of that circular entity. Right? And this continuous mode of toppling is called rolling without slipping. This continuous mode of toppling is actually essentially rolling without slipping. Or pure rolling. This is referred to as pure rolling. Right? Yes or no? Now, this continuous toppling is what we will examine in the class today. Right? It will inherit all properties of discrete toppling, because it's only a special case of discrete toppling. It's an extreme case of discrete toppling. Therefore, we'll imbibe all properties of discrete toppling as we've studied. The point of contact would have no relative motion with the surface. The nature of friction acting through the point of contact will be static. It will do no work, will produce no change of kinetic energy, and so on and so forth. Right? And yes, like he said, if this surface is fixed, this point, every point, once it comes in contact with the surface, will become the instantaneous center. Right? Say this disk, for example, is rolling on a fixed horizontal surface. Mass m, radius r, and it's in a state of pure rolling on a fixed horizontal surface. At some instant of time, we also understood that while that hexagonal body was undergoing discrete toppling, it was also translating. So it was in a state of combined motion, right? And therefore, so pure rolling is a special category of class of combined motion, right? So it will be characterized by a VCM, which would dictate translation, and omega, which would dictate reorientation or orientation, right? At any given instant of time, this, let's say A, the point of contact. From independent considerations, superimpose pure translation, which will cause A to have a velocity VCM to the right. Imagine it to be in a state of pure rotation with angular velocity omega about the center of mass. it'll have a velocity r omega to the left. This is the velocity state of the point of contact A, right? Now if it is in a state of pure rolling, the velocity of the point of contact must be 0, right? If pure rolling occurs, velocity of the point of contact relative to the surface must be 0. That means VCM minus r omega must be 0. That's the velocity of the point of contact, or VCM must be equal to r omega. VCM must be equal to r omega. That's the condition for rolling without slipping. The velocity of the point of contact, VCM must be equal to r omega. That will cause the point A to be at rest and therefore act as an instantaneous center and therefore act as the site for toppling for that instant. And every point successively, one after the other, would be offered an opportunity to become the instantaneous center, the site for toppling. Right? Sounds good? Now, again, for the time being, I'm looking at the kinematic standpoint. The causes will stay pending for a little while, right? It's possible that there could be forces and torques acting, forces causing an acceleration of the center of mass, therefore causing VCM to change, torques producing angular acceleration, therefore causing omega to change, right? No, but there would be only one point of toppling. Even in the hexagon, the entire side was in contact, but there was only one site for toppling, right? So, this VCM could change, this omega could change, right? But at every given instant, the VCM at that instant must be equal to r omega for that instant. At every given instant, the VCM at that instant must be equal to r omega for that instant, right? That means now, if it's accelerated, if this motion is accelerated, then acceleration of the center of mass is ddt of VCM. That's the acceleration of the center of mass, right? Which would be an outcome of several net external forces acting, right? And alpha, the angular acceleration, which could be owing to torques, various torques acting on the rigid body, would be d omega dt. Alpha is the angular acceleration, ACM is the acceleration of the center of mass, right? Now, if VCM is changing, omega must also change. If it continues to roll, in the event VCM changes, omega must also change, right? So if I differentiate both sides with respect to time, then we get ACM, ddt of VCM would give me ACM equals r alpha, r d omega dt, right? For every instant, VCM must be equal to r omega, and if accelerated, acceleration of the center of mass must be r times angular acceleration, right? So this is also a requirement for pure rolling in accelerated motion. Pure rolling in accelerated motion would require not only VCM equal to r omega, will also require ACM to be equal to r alpha, right? Now, say this is a body initially at rest. Let's say it's a disk of mass m, radius r, initially at rest. and it rests on a fixed horizontal surface. This rests on a fixed horizontal surface. Okay. And say the coefficient of friction, static friction, is mu. This is the point of contact, POC. At the topmost point, say there is a force F that acts on the rigid body. At the topmost point, there is a force F that acts on the rigid body. Now, suppose I know the value of F. Okay. One thing that you can physically imagine is that if F assumes a larger and larger value, then there is greater and greater possibility of slipping to occur at POC, right? Perhaps there is greater and greater possibility of slipping to occur at the point of contact, right? Now, right at the very onset, you would know whether this F is going to produce pure rolling or not. You don't know whether this F is going to produce pure rolling or not. So what you do is, if you do not know whether it's going to produce pure rolling, assume that it does. If you do not know whether it's going to produce pure rolling or not, assume that it does. Keep that assumption on active and kindled till such time there is something that contradicts this, right? We do not know whether this force F acting on the rigid body at the point shown is going to generate pure rolling or not. Okay. Now, one thing for sure, forces acting on it would be, so if you are assuming pure rolling, then at the point of contact, what must be the nature of friction? Static, right? So then again there is an issue. You don't know the magnitude of static friction, so you just assume it's F, small f. You don't know the direction. You don't even have to know. Assume any direction. The direction of static friction acting at the point of contact could be anything. Assume any direction. Assume one to the right or one to the left. It can't be acting up or down, isn't it? So let me say friction is static. Why? Why is friction static? Because there is no relative motion between the point of contact and the horizontal surface. That's why static friction. Now, under the influence of these two forces, capital F and small f, there would be an acceleration of the center of mass. There is going to be an acceleration of the center of mass, yes or no? Now, what's the equation for translation of this rigid body? Capital F plus small f is MACM. Capital F plus small f is MACM. Now this capital F. Now you want to write the torque equation. The torque equation you can write only about 2 points. Center of mass and instantaneous center. Right? Center of mass, always a safe bet. Let me write the torque equation about the center of mass. Capital F produces a clockwise torque about the center of mass. Capital F into R. Capital F produces a clockwise torque, capital F into R, about the center of mass. Small f produces an anti-clockwise torque, small f into capital R. The net clockwise torque produced is going to be F minus small f into r, yes or no? Capital F into r producing clockwise torque, small f into r producing anti-clockwise torque. How about it? That's a net torque produced about the center of mass. Yes or no? And that must be, and that produces a clockwise alpha. Clockwise torque will produce clockwise alpha, and that must be I about the center of mass into alpha. That must be I about the center of mass into alpha. What's I about the center of mass for a disk? Half mr squared. Half mr squared into alpha. Yes or no? These are basic equations of translation and rotation. But I have not yet deployed the condition for rolling. When would this body be in a state of pure rolling? What should be the condition between A and alpha? ACM must be equal to R alpha. So, pure rolling, if at all it happens, we are assuming that pure rolling occurs. We will have to justify this. We'll have to justify this, right? Now, this equation. Equation 2 I could have written as f minus small f is mr alpha by 2, right? I can add these two, and I can write R alpha as ACM. This R alpha I can write as ACM. That's the rolling requirement, pure rolling requirement. So this is like M ACM by 2. Yes or no? So this gives me twice F minus small f is MACM. Is MACM? Right? But MACM is also F plus small f. I'm just trying to calculate the value of friction force. So I'm eliminating ACM. Right? So MACM is also F plus small f. That gives me 3F equals F. Capital F is known. I mean, someone will tell you how much of force he is applying on the rigid body, tangential and at the topmost point, say for example, right? This is the thing that you do not know, right? Which you are trying to calculate in terms of capital F on the premise of pure rolling, on the premise of pure rolling. So this gives me small f equal to capital F by 3. So one thing, the fact that small f turned out to be positive means that the chosen direction of small f is right. If small f had turned out to be minus f by 3, then the direction of static friction would have been opposite. Clear? Now, look. ACM equal to R alpha is a kinematic requirement of pure rolling, right? ACM equal to R alpha. But in a force perspective, the frictional force here must be less than maximum static, right? So suppose this is N, this is mg, then this F should not exceed mu mg. This F should not exceed mu times N. So this should not exceed mu mg. Right? That means capital F should not exceed 3 mu mg. Right? Now see, on solving for small f, if you get a value capital F by 3, say capital F was given to be 15 newtons. So suppose small f turns out to be 5 newtons, right? And maximum static friction is 6 newtons. Then small f would be considered static. You know what I'm saying? I'll repeat. Suppose capital F was 15 newtons. So small f turned out to be 5 newtons. And say maximum static friction was 6 newtons. Then small f is static friction. Right? That means static friction means there was no relative motion between the point of contact and the surface. That means there was no slip. That means it must indeed have been a case of pure rolling. Therefore, our assumption would have been correct. Right? You know what I'm saying? Suppose this is 5 newtons. Capital F is 15 newtons. Small f turns out to be 5 newtons. And maximum static friction is 4 newtons. Which means small f is not static. That means our original assumption of pure rolling must have been gross and incorrect. You know what I'm saying? So this is an indirect test to know whether our assumption is correct or not. The value of friction force that you obtain, if it is not exceeding maximum static friction, then your assumption of pure rolling is right. Otherwise, it's wrong. And once you know that, suppose once you know that F turns out to be greater than maximum static friction, it has happened because your assumption was wrong. Then small f will actually be equal to maximum static friction, because then there must have been rubbing. You know what I'm saying? I'll repeat. Suppose this is 5 newtons. Suppose this is 5 newtons. 15 by 3, 5 newtons. And maximum static friction is 4 newtons. So small f turns out to be maximum static friction. That's absurd. That could have happened only if there was something wrong with our assumption. Our assumption that there was rolling must therefore have been wrong, because f is exceeding maximum static friction, which cannot happen in case of pure rolling. Right? Then the value of f that you obtain is also incorrect, because it's all obtained based on pure rolling considerations. You know that there is slipping, and if you know that there is slipping, then friction must have been kinetic. It must be approximately equal to maximum static friction. So now that's an easier case to deal with. In case you have identified that rolling does not occur. If you have identified that rolling does not occur, then it's an easy case to deal with. Right? Yes or no? Are you confused? So I quickly want to summarize this concept here. In a situation of this kind, where a force of certain known magnitude was acting as shown, right? Where we did not know whether this force F would lead to pure rolling or it would lead to slipping. What we assumed, every time we do not know whether it's going to lead to pure rolling or not, assume that it led to pure rolling. Right? And then, this of course had nothing to do with pure rolling. Assume any direction of frictional force, which then would be static. If you have assumed pure rolling, it must have been static friction. Write the equation for translation. This has nothing to do with pure rolling or not. Take the torque about a suitable point. In fact, in this case, if you have assumed pure rolling, this would be the instantaneous center. You could have taken torque about the point of contact also. That means you could have taken, say for example, you could have taken F into 2R. Is the torque, because small f will produce no torque about the point of contact, n and mg will produce no torque about the point of contact. So the net torque produced about the point of contact would be F into 2R. We are assuming pure rolling, and therefore this would have been the instantaneous center. Therefore, applying tau equal to I alpha about this point would have been legitimate. So F into 2R clockwise must have been I about the point of contact. What's I about the point of contact? 3 by 2 mr squared, right? Parallel axis theorem. This is half mr squared plus mr squared. 3 by 2 mr squared. Huh? This is not a force. This is only the effect of a force. Is this a force? In free body diagram, will you put a force like MACM? If a body has an acceleration A, will that be a force or will that be an effect of a force? No, please understand this. That's the whole premise of free body diagrams. In a free body diagrams, the forces are depicted not. MACM is not a force. It's the effect of a force. Please. Right? So this MACM is not a force. It's caused by two forces, F and small f. Got me, na? Sure about this? When we attempt to draw the free body diagram, are we going to put ACM in this? No, we are going to put F, small f, mg and n. That's it. Those are the forces acting on the rigid body, not MACM. Clear? MACM is caused by these forces, f and small f. Right? So we could have done this, taking torque about the point of contact, and we could have calculated alpha from those considerations. And then ACM would have been R alpha, and so on and so forth. And then we could have obtained the frictional force also from this equation, or this equation we could have obtained. And then, based on the value of friction force that we obtained, we would judge whether our assumption was right or not. If that value of friction force is anywhere from 0 to mu mg, then your assumption of pure rolling is right, otherwise wrong. And if wrong, then the value of friction force will not be what you have calculated. It will be mu times n. That means there must have been slipping, and the moment there is slipping, frictional force will be approximately maximum static. It will be mu n. Kinetic friction then. Then there are multitude of values that are associated with kinetic friction. Clear? Is that okay or not okay? Let me know if I could wipe this off. Right? So one thing in a situation of this kind, if a force capital F is applied like this, frictional force will act to the right. And in order that pure rolling occurs, the value of capital F should not exceed 3 mu mg. If capital F exceeds 3 mu mg, frictional force will exceed mu mg. And it will lead to slipping. Are you all very clear about this? Right? Now, see, say this body is in a state of pure rolling on a fixed horizontal surface. At some instant of time, the center of mass has a velocity VCM, and this has an angular velocity omega, right? Then of course, you know the condition for pure rolling. Pure rolling would mean VCM must be equal to R omega from instant to instant. If VCM changes, omega must also change. But at every instant, there must be compliance with VCM equal to R omega, right? So this VCM must be equal to R omega. And that will cause the velocity of the point of contact to be 0. The nature of frictional force acting here must be static. It will do no work. It will produce no change of kinetic energy. It could act to the right or it could act to the left, right? That will be dependent on the other conditions, other forces, other torques acting on the system. For the time being, don't bother about that. Now, at this instant, this is the topmost point T, right? If I have to calculate the velocity of this, I'll superimpose pure translation with pure rotation. Yes or no? Because of pure translation, it will have a velocity VCM. Imagine it to be in a state of pure rotation about the center of mass. It will have a velocity R omega, tangential velocity R omega like this. But since it's in a state of pure rolling, VCM must be equal to R omega. Since VCM, so this turns out to be 2 VCM. Yes or no? Because R omega is VCM, isn't it? Pure rolling. Nahi na, Shashi? This is the condition for pure rolling. right? So which means if this body is in a state of pure rolling, right, and if the center of mass has traveled a distance 1 meter in a given time, then the topmost point would have traveled 2 meters. See, think of it like this. What I mean is, suppose there was a plank placed on top of it, which does not slip. There is a plank that does not slip. And if the center of mass has moved by 1 meter, then the distance between t and t prime must have been, the distance between t and t prime will still be 1 meter. But all that I'm saying is the plank must have moved 2 meters. Because at every instant the velocity of the plank must have been twice the velocity of the center of mass. Therefore the distance covered by the plank must have been 2 meters. Pilots, do you understand this? Right? Now, not only that, do you also realize that say the acceleration, it's again pure rolling, say acceleration of the center of mass is ACM and it has an angular acceleration alpha. Then for pure rolling what must be required? ACM equal to R alpha. That will guarantee acceleration of the bottommost point to be 0. Tangential acceleration, right? Now the topmost point, because of pure translation, it will have an acceleration ACM. Imagine it to be in a state of pure rotation about the center of mass. It will have a tangential acceleration R alpha. But R alpha is ACM. Therefore, the acceleration of the topmost point is 2 ACM. Right? Yes or no? Say there was a situation like this. This was a pulley, fixed pulley, say. There was a mass M here. This was a pulley. Right? And there was this thread passing over this pulley and the other end connected to a mass M this way. Right? Now, if at a given instant, the acceleration of the center of this pulley was A, then what would be, and if it was in a state of pure rolling, then what would be the acceleration of the topmost point? 2A. That acceleration of the topmost point therefore would be 2A. Not only that, this topmost point is directly connected to the mass M. So if this has an acceleration 2A to the right, this will have an acceleration 2A downwards. Right? So this will have an acceleration 2A downwards. Yes or no? Right? There will be tension T in the string. There would be, if I am assuming pure rolling, there would be static friction F, whose direction I do not know, so I can take any direction, right or left. Right? Say mass of this body is capital M. This is the center of mass. Yes or no? Now what would be equation of translation for this body? T plus F is MA. Right? That's the equation for translation of this. T plus F is MA. What would be the equation of rotation for this? T into R is clockwise torque about the center of mass. F into R is anti-clockwise torque about the center of mass. Yes or no? Therefore, the net torque about the center of mass is going to be T minus F into R. And that must be I about the center of mass into alpha. That must be, so there is an angular acceleration alpha because of this torque. So that must be I about the center of mass into alpha. Now if I am assuming pure rolling, what must this be? Instantaneous center. And therefore, I could have also taken torque point. So I could have said 2 into 2r would be I about the point of contact into alpha. Why? Because friction produces no torque about this point. Mg produces no torque about this point. N produces no torque about this point. Yes or no? See? And about the center of mass, N and Mg pass through the center of mass. They produce no torque about the center of mass or through the point of contact. You know what I'm saying? So in any case, say this is the equation for rotation. This is the equation for rotation. And what would be the equation for rolling without slipping? A must be equal to R alpha. That's the physics involved in this problem for this body. Now for this body, T is the tension acting down upwards, small mg downwards. So mg minus T must be m into 2a. It does not matter. I mean, if it's a disk, it will be half mr squared. If it's a ring, mr squared. If it's a sphere, 2/5 mr squared, and so on and so forth, right? Now, can I wipe this off? Is this understood by all? See, suppose this body is rolling without slipping and it has a VCM and omega. It has a VCM and omega and it's rolling without slipping on a surface which is not fixed but a moving surface. Say this is a surface with a velocity v0. v0. Say this surface is moving to the right and it has a velocity v0. Yes or no? Now, there would be then a revised condition for rolling without slipping. For pure rolling. See, forget the surface for a while. Just look at the point of contact. The point of contact, because of pure translation, has a velocity VCM to the right and has a velocity R omega leftwards. The net velocity of the point of contact, therefore, must be VCM minus R omega to the right. Now, in order that there is no rolling, there must be no relative motion between the point of contact and the surface. Therefore, the velocity of the point of contact must be the same as the velocity of the surface. Right? Isn't it? The velocity of the point of contact, therefore, must be the same as the velocity of the surface in order that there is no relative motion between the point of contact and the surface. Right? Yes or no? So, VCM minus R omega must be equal to V0. This then becomes the revised condition for rolling without slipping. Yes or no? So far so good. Suppose the surface had acceleration, right? So this is the surface and say the surface was made to move with a constant acceleration a naught to the right. Suppose the surface was made to move with a constant acceleration a naught to the right, and say the acceleration of this was ACM, right? And say we do not know that, say the angular acceleration was alpha like this. I could have also taken it that way. Suppose it was like this. Okay. Then look at the point of contact. Damn thing. Then because of pure translation, ACM to the right. Imagine it to be in a state of pure rotation about the center of mass. It will have an acceleration R alpha to the right. If alpha was taken this way, then it would have been ACM minus R alpha to the right. Right? I'm just giving an example. So don't assume that alpha has to be like this. It could have been like this, and then this would have been ACM minus R alpha. Then the revised condition, if it has to roll without slipping, then acceleration of the point of contact must be the same as the acceleration of the surface. So this then must be equal to A naught. This will be a requirement for pure rolling then. Do you all understand this? Yes or no? See, say in a situation like this, say there was a disk. There was a disk, okay, and it was comfortably resting on the surface. Okay. And the mass, say this disk had mass m and radius r, uniform disk, mass m and radius r. Okay. And the surface was imparted an acceleration a naught to the right by some means. By some mechanical means, the surface was imparted an acceleration a naught to the right. Now, first thing, I want to know if this body would roll or not. I want to know whether this body would roll or not, right? So if I see, if this acceleration is very large, you know it will slip. If this acceleration is very small, it will roll, right? So as the value of this A naught goes on increasing, this body will become more and more vulnerable towards slipping, right? So in any case, there is a maximum A naught that will be favorably disposed towards pure rolling. That will be favorably disposed towards pure rolling. Yes or no? Right? Now, let me assume pure rolling. Let me assume pure rolling. If I am assuming pure rolling, then one thing, the frictional force here must have been static and would either act to the right or to the left. Let me assume that friction F acts to the right, and let me assume that it is static. Till such time we do not know, we will assume that it is static, right? Now if I have to write equation of motion for this, what would be the equation of motion for this? F equal to MACM, right? Translation would mean F equal to MACM. Right, Diptesh? There is mg like this, there is normal reaction like this. N and mg produce no torque about the center of mass. N and mg produce no torque about the center of mass. The net torque produced about the center of mass is by friction. And in which sense? Anti-clockwise torque. What's the magnet? Yes. That is, if I am looking at a frame of reference attached to this, I'm looking from the ground frame of reference. Pseudo force will be if I look at this body in respect to an observer attached to this accelerated frame, then pseudo. If the observer is accelerated, my observer is the ground observer. No pseudo force then. It's an unaccelerated frame in which I'm writing its equation. So no pseudo force, right? So this is my observer, by the way, right? Inertial frame of reference, so no pseudo force. Now, so talk about the center of mass. F into R is I about the Cm into alpha, right? Anti-clockwise torque is I about the Cm, say half mr squared into alpha. Yes or no? So that gives me F equal to mr alpha by 2. This is translation, this is rotation, but now there is a condition for pure rolling. Acceleration of the point of contact must be equal to the acceleration of the surface, A naught, right? What's the acceleration of the point of contact? ACM because of, ACM because of pure translation, plus R alpha, imagine it to be in a state of pure rotation, and this must be equal to the acceleration A naught. This is the condition for pure rolling. Henceforth, if I say rolling, it would mean pure rolling. I will not say pure and impure rolling. Rolling would mean very pure rolling. Okay? If it rolls, means it rolls without slipping. That is what we will imply. So I don't want to always, add bulk to what I say or write. Now, this gives us an opportunity to compute F, say for example, right? Because I could write R alpha as A naught minus ACM. A naught minus ACM, this R alpha. This R alpha I write as A naught minus ACM. And, No, of course not. This MACM I can write as F, small f, right? This MACM I can write as small f. F equal to M A naught by 2 minus F by 2. MACM is small f, so minus F by 2. Oh, you mean you after calculating. So F then turns out to be A naught by 3 into M, MA naught by 3. 3F by 2. So F is MA naught by 3. Yes or no in this case, for this situation, for example. Right? I mean, there is no physics here. This is all algebra. This was physics, this was physics, this was physics. Everything else that I have done is algebra. Clear? Now, I can calculate maximum static friction, mu mg for example, in this case. And suppose this is 10 newtons. And this turns out to be 5 newtons. Then indeed this is static friction. That means my condition, my assumption is right. Suppose this turns out to be 10 newtons, mu mg. Right? And this calculation of small f as MA naught by 3, this turns out to be say 5 newtons. That means this is static friction. That means there must have been no relative motion between the point of contact and the surface. That means indeed there must have been pure rolling. That means indeed our assumption must have been correct. Right? But suppose mu mg is 10 newtons and this turns out to be 10.5 newtons. That means there must be something wrong with our assumption. That means rolling did not take place for that value of A naught. Right? Now the question is, what's the maximum value of A naught that will promote or that will be favorably disposed towards pure rolling? One in which this does not exceed mu mg. will give me a limit on A naught. That means A naught should not exceed mu g by 3 mu g. As long as A naught is less than or equal to 3 mu g in this case, for this situation, these are not values that I want you to remember. I'm just giving you the ideas, right? I don't mug up these values. I mean, instead of a disk, you could have a sphere, or you could have a ring. So these are only ideas to be born in your head, right? So which means, just to suggest that there is a maximum limit of A naught. The maximum limit of A naught in this case for this situation is 3 mu g. Anything in excess of 3 mu g would promote slipping. A naught not exceeding 3 mu g would be favorably disposed towards pure rolling. Do you all understand this? So what? Which means no matter what the mass of the disk is, see, because eventually algebraically there is a division by mass, the force will be directly frictional force will be directly proportional to mass. So the acceleration produced by friction force will be independent of mass, isn't it? Because eventually you will divide by mass, that's algebraically speaking. And otherwise also, see, this acceleration for any mass will lead to the same condition, as long as we are talking of the same geometry, everything else remaining the same, will lead to the same condition. There is, see, if there is an increased mass, there is a proportionally increased friction force. The equation of motion I wrote for translation, that's proportional to n. Everything increases in the same proportion as m increases. Therefore, it will turn out to be independent of m. Torque, net translation, everything is proportional to n. So I could have actually spoken of force per unit mass, which would be the same, right? Now, say this is a disk, uniform disk of mass m and radius r. Uniform disk of mass m and radius r. Clear? And there is a rough surface, fixed surface. And say mu is the coefficient of friction. And it is set in a state of pure translation. Every point of the surface has the same velocity v naught to the right. Set into pure translation. It is set into a state of pure translation with every point having the same velocity as the center of mass, say v naught. Okay. Now, the lowest point has a rightward velocity with respect to the surface. So there is relative motion between this point and the surface. So frictional force would be kinetic in character and would act to the left. So do you realize that frictional force in this case is mu mg, mu times n, n is mg in this case. Clear? So it's going to produce a leftward acceleration mu g. It will produce a leftward acceleration mu g. This will reduce the velocity of the center of mass. It will retard the velocity of the center of mass. Right? Not only that, mg produces no torque about the center of mass. N produces no torque about the center of mass. The net torque will be produced by F about the center of mass. F into R. F into R. Clockwise torque will produce a clockwise alpha. Clockwise torque will produce a clockwise alpha. Right? And therefore this clockwise alpha will build a clockwise omega in the rigid body. Yes or no? Right? So after a while, let's say this rigid body develops a VCM and an omega. This is the rigid body develops a VCM and an omega. Clear? T seconds later, this was an instant of time t equal to 0. There is a retardation mu g produced. So velocity of the center of mass t seconds later would be v naught minus mu gt. V equal to u plus at. A is minus mu g in this case. A is minus mu g in this case. Yes or no? Yes, sir. Right. Omega would be, the initial omega is 0 because, right, omega naught is 0. Omega would be omega naught plus alpha t. Omega would be omega naught plus alpha t. Omega naught is 0. Right. So this is going to be alpha t. And how's alpha calculated? Alpha would be, take torque about the center of mass. F into R is the clockwise torque about the center of mass divided by I about the center of mass. I about the center of mass is going to be half mr squared. By applying tau about the center of mass equals I about the center of mass, which is half mr squared into alpha, I can calculate the angular acceleration. Angular acceleration. Yes or no? So clockwise angular acceleration is known to us. So which is like 2f by mr. Yes or no? F is mu mg. So this is like 2 mu g by r. 2 mu g by r is the angular acceleration, right? Yes, So once I know alpha by taking torque about the center of mass, this omega t seconds later is alpha, which is 2 mu gt by r. Yes or no? Now do you realize that VCM is decreasing with time and omega is increasing with time, right? In this case, see, r omega at any given instant of time is 2 mu gt. R omega is 2 mu gt at any given instant of time t. R omega, and VCM is V naught minus mu gt at any given instant of time t. Now, so R omega is increasing with time linearly, and VCM starting from a value V naught is linearly decreasing with time. At some time t equal to t naught, do you realize R omega and VCM become the same? See, VCM is decreasing with time, R omega is increasing, the two must intersect somewhere. That means at some instant of time t naught, VCM and R omega must become equal, right? Has to become, and that's the instant of commencement of pure rolling. That's the instant of commencement of pure rolling. This t naught is the instant of commencement of pure rolling. right? So at time t naught, rolling commences. Time t naught, what happens? At time t naught, r omega at time t naught will become 2 mu g t naught. 2 mu g t naught. VCM at time t naught will become V naught minus mu g t naught. For pure rolling, VCM must be equal to r omega. That means 2 mu g t naught must be equal to V naught minus mu g t naught. Right? Or that gives us t naught equal to V naught by 3 mu g. T naught equal to V naught by 3 mu g. At this instant of time, pure rolling starts. At this instant of time, pure rolling starts or commences, right? Now, greater the value of mu, the lesser would be the time it takes for commencement of pure rolling. Greater the value of mu, the lesser will be the time it takes for commencement of pure rolling, right? As mu increases, the time t naught for commencement of pure rolling will decrease. The time t naught for commencement of pure rolling will decrease. Now, what did mu naught do? See, when the motion started, what was stronger? Translation was stronger and rotation was weaker. Right? There was lack of parity between translation and rotation. Right? What did mu do? It weakened the stronger and it strengthened the weaker to bring about parity, so that rolling could commence, so that at some instant of time VCM could become equal to r omega. Omega was enhanced, whereas VCM was depleted. Eventually VCM turned out to be r omega, right? So it brought its children at par. VCM and omega were brought to par. VCM turned out to be r omega, and commencement of pure rolling took place. So now, again, so if mu is more, the time it takes for commencement of pure rolling will be less. Friction, therefore, is a friend of rolling. If mu is infinity, then the moment you set it up into pure translation, at that very instant, pure rolling will commence. If t is infinity, theoretically, right? Isn't it? So, friction will always support pure rolling. If it finds that it has to do something in order to produce pure rolling, it will do that. It knew that it had to build up omega, so it acted leftward so that it could build omega this way. It knew it had to weaken this, so it acted opposite to VCM, and then eventually brought about VCM equal to r omega, the condition for pure rolling. Yes or no? But until the time pure rolling took place, friction was kinetic in character. The moment rolling commenced, this changed phase. It became static. It assumed a value less than mu mg, because mu times n. Why? Because it was not required to that extent. Its direction then also would be commensurate with one that will proliferate pure rolling only. Yes or no? Now I'll tell you the story after pure rolling, what happens, right? If you give me a few minutes, let me have the pleasure of taking you through that story all by myself. Okay, can I wipe this off? See, see, we started with this V naught, pure translation. right? At some instant of time, t, let's say v1 was the velocity of the center of mass, omega 1 was the angular velocity built at some instant of time t, right? That must have been a state prior to commencement of pure rolling, prior to commencement of pure rolling. At some instant of time t naught, omega became omega, VCM became VCM. Rolling commences. VCM is rendered equal to R omega. Point of contact, point of contact, point of contact. This is state 1. This is an intermediate state 2. This is the state where rolling commences. This we figured out is some V naught by 3 mu g, right? Don't mug up these values. Okay, they are only meant to be instructional for the time being. Now, between state 1 and state 3, there is rubbing between the point of contact and the surface, right? There is rubbing between the point of contact and the surface. Friction hogs up energy. There is rubbing between the point of contact and the surface, therefore the total energy of the system decreases, kinetic energy decreases. What's the kinetic energy here? Half m v naught squared. What's the kinetic energy here? Half m vcm squared plus half ICM omega squared. Which kinetic energy is more? This is more. Why? Because between this state and this state, friction has eaten up kinetic energy. There was rubbing between the point of contact and the surface. So this kinetic energy will be less than this kinetic energy. The difference would have been the work done by friction. Work done by friction would be this minus this. Negative work is done by friction. That's why change in kinetic energy is negative. Decrease in kinetic energy means work done by friction must be negative. Right? And again, between this state and this state, this has more kinetic energy compared to this, because again, from 2 to 3, there still has been rubbing between the point of surface and the ground. Right? So more amount of energy is hogged up. Clear? Now, the important thing is, all along, no matter what, mg has been acting this way, n has been acting like this. Friction force, in this case, say for example, kinetic friction acting this way, right? What's the torque about, net torque about the point of contact here? Bes, Asura. 0, yaar. F passes through this point. So, net torque about this point created by friction is 0. By mg 0, by n 0, because the line of action of n, mg and f all pass through the point of contact. Torque about the point of contact is 0. In this case also, f like this, n like this, mg like this, and all through the journey, whether rolling commences or not, the net torque about the point of contact continues to be 0 at all times. And therefore, angular momentum remains preserved. Angular momentum about the point of contact, by the way, not about the center of mass, because about the center of mass, there is a torque F into R. Therefore, angular momentum about the center of mass is not conserved, but angular momentum about the point of contact is certainly conserved. Whether I take a state prior to pure rolling or after pure rolling or the state of pure rolling, between any two states, I can conserve angular momentum about the point of contact. So, L about the point of contact must be constant. Yes or no? Okay. Now tell me, what's the angular momentum about the point of contact in this case? mv naught into r. Right? We started with mv naught into r. What's the angular momentum about the point of contact in this case? mv1 into r plus ICM omega 1. Right. Shit, damn thing. Yeah, there's a small little creature bothering me too much. mv1 into r plus ICM omega 1. And that must also be angular momentum about the point of contact in this state, which is how much? mvcm into r plus ICM omega. Right. Right? So, suppose they wanted you to calculate without using equations of kinematics, v equal to u plus at, etc., the omega or VCM at the instant of pure rolling. Suppose they wanted you to calculate the VCM at the instant of pure rolling. You know, either you could have used the earlier equations that I said, VCM is V naught minus mu gt and omega is omega naught plus alpha t, and when VCM becomes equal to r omega, I can find the time when pure rolling starts, and then VCM is V naught minus mu gt, I can calculate the VCM when rolling starts. That's one way. Or I could have computed VCM at the instant of pure rolling by simply deploying conservation of angular momentum about the point of contact. This is equal to this, right? And when rolling starts, omega can be written as VCM by R. When pure rolling starts, this omega can be written as VCM by R. And from this and this, I could calculate VCM when pure rolling starts. I could have, without finding the instant t when pure rolling starts, I could have still computed the VCM without knowing that instant, using conservation of angular momentum about the point of contact, yes or no? Clear now? Now, so far so good, right? From this state to the state when rolling commences, there has been loss of energy, right? But angular momentum about the point of contact remains the same, right? Because there is no torque about the point of contact. Friction, mg and n all pass through the point of contact, so tau about the point of contact is 0, L about the point of contact must be constant, right? Now that's, I didn't have space to draw that. That's why I said I'm going to tell you now what after pure rolling, right? So at some instant of time, pure rolling starts. This instant t naught when pure rolling commences. Now, I want to know what's going to transpire after this. One, this is the POC. Velocity of the point of contact will be maintained 0 at all times, so that there is no relative motion between the point of contact and the surface. Pandit ji, पूजा पाठ करके ठीक से कल खेला शुरू नहीं करवाए, हार गई कालू लोग से कल. जैसे रुको ना, आज तुम लोग को कितने बजे तक पढ़ाता हूँ, माथा मेरा वैसे ही गरम है. वो उनको मैं बोल दूंगा, वो भी गुस्सा है, उनको बोलूंगा नहीं तो I'll transfer the load to him. I'll tell him to teach you till 11 o'clock today. You made India lose. You'll have to pay for it. And Panditji, you're not doing your puja part properly. Huh? No. Okay, get back to this. So, and the nature of friction acting must be static here, right? If friction could be acting to the right or to the left, and it could have any value from 0 to mu n, right? Suppose this was horizontal and suppose there were no other forces acting. So now the case I'm going to describe is suppose there are no other forces. So don't take this as cardinal and don't take this for all possible situations. Suppose no other forces were acting. No other force was acting. No other force means only mg, n and friction force are acting, right? Suppose no other force acts. Now my question is, and this surface is horizontal and fixed. Now my question is, and it's also your question, what's the direction of frictional force? What's one thing, frictional force will be static. Work done by the frictional force is going to be 0, because the point of application of the friction force is not getting displaced, it's instantaneously at rest. Velocity of the point of contact is 0, so power associated with the frictional force is F into velocity of point of contact, which must be 0. That's a force into velocity. So power associated with friction force is 0. So work done by friction force must be 0. No change in kinetic energy is brought about by friction force. Right? Now, whether friction will act to the right or will act to the left. Yes, so let's have a referendum. How many of you think static friction will act to the right? How many of you think it will act to the left? No one should think it will act up or down. So right. 3 people are right. I'm not saying they are right. 4 people are right. 6. Total number of votes for right, 7, 8. Are you following them or are you following your own instincts? Own instincts, Prince. And left? Okay, so others are neutral. Others think it will act up or down. No, everyone has to commit. Either right or left. Again, I'll take a fresh referendum. How many to the left? How many to the right once again? Only the numbers have grown, but still not the universal set yet. No, all of you will have to commit. Right or left? Right once again. Okay, greater numbers. Left once again. Some people are still left. Not yet. Not yet. You can't be non-committal on this. You will have to commit to one thing or the other. Once again, right. Left. Now, there is steady state conditions reached here. And there will be no further change, no matter how much I insist. Okay. Suppose I take the right as right. Okay. Suppose friction acts to the right. And VCM has been rendered R omega courtesy friction force. Courtesy friction force, VCM has been rendered R omega, right? VCM built omega and killed frictional force built omega but killed VCM, so that VCM could become equal to R omega at some point of time, right? Now, suppose friction acts to the right. It will increase VCM. VCM increases. Yes or no? This friction produces a torque like this. So it will produce an alpha like this. Torque about the center of mass is anti-clockwise. So it produces an angular acceleration like this, which is opposing omega. So There is angular retardation, so omega will decrease. Jolly shit. This equation gets disturbed. If this increases and this decreases, can they be equal an instant later? That means the condition for rolling has been disturbed. And friction has done that, yaar. Friction was the father of pure rolling here. How can it kill its own baby? Right? Friction was instrumental in bringing about pure rolling. Now by acting to the right, it's disturbing rolling conditions. So it cannot act to the right. Yes or no? And therefore you would be tempted to believe it must act to the left. Suppose it acted to the left. Suppose it acted to the left. Then what will happen to VCM? Decrease. VCM will decrease. It will produce a torque like this, an alpha like this. So omega will increase. This condition will once again be disturbed. Rolling will be disrupted. So in this case only, if there were no other forces acting, friction force will neither act to the right nor to the left. That means it does not matter whether it acts to the right or left in this case. When will it not matter whether if F was 0? F equal to 0 is also a case of static friction, yes or no? Anywhere from 0 to mu mg is static friction. So this is one possibility for static friction. In this case, static friction will be 0. Therefore, its action to the right or to the left is immaterial, inconsequential. Right? If there were no other forces acting on it. By the way, that's the condition that I have deployed. If there were other forces, then friction would act in a manner that rolling is preserved. That's another issue. But otherwise, in this case, static friction would be 0 in value. Now, whether you take it acting to the right or to the left, it couldn't matter at all. Right? And therefore, VCM will remain the same, omega will remain the same. Why? Because if F is 0, ACM will be 0, alpha will be 0. If ACM will be 0, VCM will be preserved. And if alpha is 0, omega will be preserved. Yes or no? So the body will continue to move with the same VCM and with the same omega. The body would continue to move with the same VCM and with the same omega. Why? Because if F is 0, ACM will be 0. So VCM will be constant. Right? If F is 0, ACM is 0 or VCM is constant. Right? If F is 0, alpha is 0 or omega will be constant. If angular acceleration is 0, then omega will be constant. Therefore, it will continue to roll with the same VCM and with the same omega, maintaining its kinematic status at all times. Of course, in real life it does not happen because there is an air drag which will produce a torque about this, and its VCM and omega will keep getting, it will come to rest because it will have to do work against air drag, and negative work would be done by air drag, and it will eat up all the kinetic energy. Eventually it will come to rest permanently. But in an ideal situation, if air drag is ignored, it will continue to roll on forever. Got me? See, in earlier times, Harbhajan used to bowl a ball. नहीं यार तीसरा है. Where the ball would stop in front of the batsman. You know. Sorry. No, he could bowl that because he never studied physics. Otherwise, if he had studied physics, then during bowling he would do that calculations. And Sardarji would do wrong calculations. No. Sorry. I take back my words. See, what he did was, he did the following. He imparted a velocity v naught to the right to the center of mass, and a reverse spin omega naught, like that, right? Somehow he managed with some deftness, he managed this. Okay, it had a center of mass to the right and it spun backwards, reverse spin, but it translated to the right, right? And then, if this was the batsman, just in front, I'm sorry, it's not bigger than the batsman. It stopped. Okay. That means velocity of the center of mass was 0 and omega was 0. Underarm. Hurry, yaar. So question is, there must have been a special pair V naught and omega naught that led to this. A special pair V naught and omega. Not every V naught and omega naught will lead to this. A special pair V naught and omega naught that must have led to this. Hey, realize that about the point of contact, the angular momentum must be conserved, because frictional force passes through the POC, produces no torque. Mg and N pass through POC, produce no torque about POC. L about POC must be constant. Now, in this case, what's the net angular momentum about the point of contact? Mv naught R clockwise, ICM omega naught anti-clockwise. ICM omega naught anti-clockwise, right? In this case, 0. So this must have been 0, equating angular momentum about the point of contact in this to angular momentum about the point of contact in this. So this must be the relationship between V naught and omega naught, in order that it could stop in front of this piddly batsman, West Indian. Huh? Damn thing, yeah, damn thing. I'll put a tantric for him. Huh? Imagine, he was not supposed to be there. He was born just to kill India. He was brought all the way from that land to this. He didn't even come out of his jet lag and started. In any case, so this is, huh? No, see, I'll tell you one very simple thing. If there is a match of this stature going on in our own land, with BCCI having all the power and pelf, being the most powerful body, then of course, they should deploy Indian tactics. They should buy these guys out. How much do they cost, yaar? Few bananas and few that's it. एक आदमी को 3-4 पेड़ केला का दे दो तो खुश है. All monkeys, yaar, Give them some peanuts, some bananas and some money. They'll be happy. Huh? These guys survive on a bowl of rice. I mean, barrels of rice, in fact. They must. We could have bought them out. Realized so much of money was earned by so many people, Wankhede Indians, assembling only to see India win. That's all. By hook or by crook. Fair or unfair. Okay. Everyone was anyways very sad yesterday because of the Girish Park incident, the bridge incident. And at the end of the day, if at least, that this could have been a tribute to so many who lost their lives. Sorry. This is what happens, right? So you understand what to how to apply conservation of angular momentum, right?